Hello chemistry students. In this video I'm going to go over the electron cloud model of the atom, as well as maybe get into electron configuration a little bit, but this is likely part 1 of the video and there will probably be a part 2. So I'll start off with this. So we have a mathematician by the name of Erwin Schrödinger that took the stuff from the other scientists, Louis de Broglie as well as Niels Bohr, and took that information and put it into something that would give us a way to describe the atom, or describe the electrons around the atom in three-dimensional space. And so I'm going to start out with this y equals mx plus b thing. You might be like, oh, that's the equation for a line. Okay, good. So far. We'll make it through. Now, if you look at Schrödinger's equation, and yeah, it is kind of big and scary, and I remember every time I would see the letter there for the wave function when I was taking physical chemistry, I would start to have, kind of a almost anxiety response to it. It's like, oh no, here comes that again. But anyways, you can look in here and you can see the x, the y, and the z. And if you think about that a little bit, like, well, what's that? Well, that's directions on a Cartesian coordinate graph. So like, x and y axis, and then there's a z. And then if you square those variables, you get things that are parabolic, or like an x squared function where it curves. Okay, so when you get x, y, and z squared all together, well, we're describing something kind of spherical in space. Okay, so and we're not going to solve the wave functions. I'm just going to show you some of the shapes that that arise from the solutions to the wave functions. Okay, so the Bohr electron orbits are not really orbits. Okay, now we're calling them orbitals, and those orbitals are three-dimensional areas in space, and they're described by mathematical formulas. They do surround the nucleus, but they're not rings or orbits. Okay, and the good news is you're not going to have to learn the formulas unless you go on like I did and maybe major in chemistry and take physical chemistry or something like that. We're going to learn some of the shapes, and this model of the atom is known as the quantum mechanical model or the electron cloud model of the atom. And again, that's you have a three-dimensional area of high probability of finding an electron, described by Schrödinger's equations. All right, so in that three-dimensional model, there are four, well, I'll go over the first four sublevels. There's actually more than that. Those are S, P, D, and F. And each sublevel has multiple orientations of or orbitals around the origin of the X, Y, Z coordinate plane. So we'll jump out here to the Orbitron thing and take a look. And hopefully everything will pop up and it'll be great. Okay, good. All right, so here it is. And so you can see a 1S here. And it's like, well, that's a pretty boring shape. And there's only one orientation for the S because it's round. Okay, so three-dimensional, it has three-dimensional symmetry, so there's no way to arrange it differently around the axis. Okay, 2S looks similar. There is some internal structure, but this is another round one, maybe a little bit bigger than the 1S. And then the 2Ps, oh, look at that. Those kind of have a couple of lobes on them. And there's one oriented on the Z-axis, and one oriented on the X-axis, and one oriented on the Y-axis. So they're very similar, and yet they're oriented differently. Now, again, this is understood as an area where you would be, within this shape, you would be highly likely to find the electrons that are associated with this particular orbital. And within an atom, these are kind of like nesting dolls or something, where these might be present, as well as an atom could have some 3s and 3p and 4s and even 4p electrons present as well, and those might be around and maybe even within these orbitals, and these would, all be centered around the same nucleus, so there'd be a lot of things overlapping if you're trying to imagine all of these orbitals within an atom. And the larger the atom, the more levels there would be present. All right, so some patterns kind of emerge. S continues to be a spherical shape, more internal structure as you go up to higher levels. And then 3P, you can kind of see still the same kind of lobe thing going on. The colors are here just for artistic effect. I don't think the orbitals themselves would have a color if you could see them, and they would be incredibly small anyways. Okay, and then the 3Ds. Now, the D sublevel, we're getting into some different shapes here. So kind of like the Ps, and then they have lobes, but it's 4 lobes instead of 2, and then they orient in different ways. And then the DZ squared orbital is kind of special in that it looks like this instead of like the remaining ones. All right, and then the 4th level, there's an S, here's a P, here's the Ds. So a lot of similarities there, some kind of neat structural things going on. And then the F orbitals, you also see those. So there are 7 of those F orbitals. And then we can get into some more exotic things. I'll just take you through and show you. So there's the 5G, there's 9 of those. And then there's also, well, yeah, going to some of the craziness here. So the 6Gs and then the 7Gs. All right, so cool stuff. How is this practical to us? So we'll have to come back and revisit a little bit. All right, let's take a look at the structure of the electron cloud. So the first level of structure is the energy level. And the energy level is representative of the distance of the electrons from the nucleus. So the larger the energy level, generally speaking, the farther on average the electrons within that energy level will be away from the nucleus. Okay, values of N are always going to be positive integers starting with 1. And the number of orbitals per energy level, or sometimes energy levels are called shells, will be equal to N squared. So like if the energy level is 2, then there are 4 orbitals possible. 2 squared is 4. Okay. Then within each energy level, there will be energy sublevels, or subshells, they're sometimes called. And that indicates the shape or shapes of the orbitals. And the number of orbital shapes present in each energy level is equal to N. And the shapes in the first 4 subshells, like we've already seen, are S, P, D, and F. All right. So energy levels, maybe a visual of that is kind of like the Bohr model: first level, second level, third level, fourth level. But remember, within each of those, there's all those wild-shaped orbitals and everything. All right. N is also known as the principal quantum number. Okay. And we looked at the S orbitals, the spherical shaped one. Okay. And S is present on every energy level. And the larger the energy level, the more S sublevels will be present. So if you have an element on the 3rd row of the periodic table, it will have at least 3, well, it'll have 3 s sublevels. Okay, and s orbital, like all other orbitals, can only hold a maximum of 2 electrons. All right, the p orbitals we've already seen. All right, so you have all 3 orientations there, and then 2 electrons in each. So that leads to a total of 6 electrons being held by, or possibly being held by, a p sublevel. Okay, and the first energy level that p is found on is the second energy level, n equals 2. All right, so s sublevel appears on the first energy level. Remember, the number of orbitals possible is equal to n squared, and there are 2 electrons per orbital, so the total number of electrons here is 2. Then on the second energy level, p sublevels can also appear, and so on the second energy level there would be 3 p orbitals and 1 s orbital. That would be 6 electrons in the p and 2 in the s for the second energy level. And in the third energy level, the d orbital appears. The orbital also has s and p sublevels on it, and so anyways, within the d's there are 5 orbitals and 10 electrons possible to be occupying the d orbital. And then the f orbital appears on the 4th energy level, 7 possible orbitals there, and 14 total electrons can fill up the f sublevel. Right. The orbital quantum number is what indicates the sublevel or the subshell, and that is the symbol for that is an L, and that's going to indicate whether, what shape it is, like SPD or F. Values go up to n minus 1, so like 0 for that is, and starting from 0, 0 is the S, 1 is the P, 2 is D, and 3 is F. All right, and then there's a third quantum number, which is the magnetic quantum number, and that's an M sub L, and that indicates the orientation in space. So S has 1 orientation, P has 3, D has 5, and F has 7 orientations or shapes, like we saw when we looked at the Orbitron website. And that identifies which specific orbital an electron might be in. And then finally, there's a last point, which is the spin of the electrons within the orbital. So within each orbital, a single orbital can hold 2 electrons. And then for those 2 electrons to occupy a single orbital, we'll learn later, they have to have, or a while later, they have to have opposite spins. So one has to be spin up and the other has to be spin down. So that is the 4th quantum number. It's the spin, which is the spin quantum number, and that's M sub S. And the values for that that are possible are either plus 1/2 or minus 1/2. And all electrons spin regardless of whether they're bonded to something or part of an atom or not. And the way this was observed was placing atoms within a magnetic field, and that causes the electrons to align either up or down, and that gives you the spin up or spin down. So the possibilities there again are plus 1/2 and minus 1/2, and we represent those with arrows either pointing up or down. That ends this video. Thanks for watching.